Okay, so now we are going to take a look at some problems in permutations and combinations, and hopefully this will be a good refresher for you for some problem solving strategies. Okay, so let us look at this first question. They ask you find the number of arrangement of the 9 letters of this word. So when you get problems about letters in a word, which is reminiscent of tutorial S1 question 3, it actually helps to take note of the repeated letters. So let us write out the letters, see which letters are repeated. And you see that there are 2 S's, right? So we know that we need to take care of this. So keep that in mind. And firstly, let us do part A, which is very simple. So the number of ways to permutate this particular combination with no restrictions whatsoever. I have 9 objects in total, right? Check 1, 2, 3, 4, 5, 6, 7, 8, 9. Yep. So I have 9 letters in total. And out of those 9, these 2 S's are identical. So because the other letters are distinct, but these 2 objects are identical, we divide this by 2 factorial. And this is going to be 18140. So quite a simple one, just a direct recall of the formula. And next, this is where it starts to get slightly tricky. Now it says I want the 2 S's, so I've already put the S's in orange, right? So I want the 2 S's are not next to each other, and these 4 letters I, N, P, T must be together. So what we can do is, let's first think about what can be together. So the way that we can think about it, right? Let's say the 2 that must be separated are the troublemakers. So because they're the troublemakers, we'll deal with them last. These 4 in this box here are the ones that are well behaved. They can be together. So because they are well behaved, we are going to reward them by dealing with them first. So we are going to group these 4 as 1 unit. Okay, and as a result, we can start to write it out, right? So don't be afraid to write out to help you. So actually, I don't need so much spacing. This is just 1 unit. Okay, treat this as 1 unit because they cannot be separated. Okay, they all must be together. Next, we'll deal with the S's last. So notice, after this IMPT, I have a couple of other letters, right? I have O, E, R. Is that it? Yes, that's it. Okay, so let's not worry about the troublemakers first. Let's deal with all the well-behaved ones first. So currently, what do I have? Currently, notice how even though these 4 are 1 unit, they move as 1 unit, but you can permute these 4 in any order within this box. So within this box, I have 4 factorial. Next, how many units do I have in total here? This box is 1 unit, so we count it as 1 unit. This letter is 1 unit. This letter is 1 unit. This letter is also 1 unit. So I have 4 units, and these 4 units must be permuted among themselves. Then we deal with the troublemakers last. Now, the 2 S's are not next to each other, so in order to separate objects, we use the method of slotting. And we're going to slot them now. So how many slots are there? Possibly, I have 1 slot here, 2, 3, 4, and 5. So I have 5 possible slots, and I have only 2 letters to slot, right? Because no matter which 2 of these 5 they are slotted in, they are going to be separated, confirm. So it's 5, choose 2, and that is all. So this is going to be, if you press your scientific calculator, that's going to be 5760. So just a couple of learning points from this particular question alone. You remember that everything that is together, you group them together, and then you treat it as 1 unit, and then you permute the number of distinct units first. Any slotting that you need to do, you do last. Okay? And remember, within 1 box, within 1 unit, if there are distinct objects within that unit, you still must permute them. So the order of permutation, I would say there is no specific order in which you must write it because after all multiplication is commutative. But the best way to think about it for yourself so that you don't overcount or undercount is first you permute anything that is within a unit, within a box. Then you permute the total number of distinct units, and any slotting gets done last. Okay? Keep this order in mind. Now, part C of this question is very reminiscent of tutorial S1 question 3C. So, when you choose a 4-letter code word, you need to be aware, okay, there are a couple of cases. Actually, in this case, there are only 2 cases. Yeah, because there's only one repeated letter. In your tutorial S1 question 3, hang on, let me put it up. In your tutorial S1 question 3, there was actually a lot of cases because I have delectable, right? So if I try to write this word out, delectable. If I try to write this word out, because I have 3 E's, right, means I must consider 3 cases. One is that no E's are chosen. One is that all 3 E's are chosen. One is that 2 of the 3 E's are chosen. But in this case, I only need to consider 2 cases because there are only 2 S's. One letter is repeated only twice. So I only need to consider 2 particular cases. One is that all the letters are different. So let us say case 1, all letters are different. And do note that case 1 includes the possible case where one of the 2 S's is chosen. It is okay as long as all the letters are still different. So the number of ways for case 1 is going to be, I have 8 distinct letters to choose from, right? Because I can only choose from these 8 on top in order for all 4 letters to be different. So, sorry, I have 8, and out of the 8, I need to choose 4, right, to make a 4-letter code word. And then after that, this is my choosing. And then what's the next step after that? I permute all my distinct units. So in this case, there are 4 distinct units, right? So I need to add a 4 factorial at the back. And this is 1680. So this is the first case. The second case, because there are only 2 cases, is obviously the fact that both S's are chosen. And think about it for a moment. What would be the number of ways for case 2? So if both S's are chosen, means that, let me just erase this. So both of the orange things are chosen. So how many more letters do I have to choose from? I can choose from these 4 or these 3, because both of these confirm plus chop, they got their places locked in already. So actually, right, how many places, because 2 of them, they already have their places choked. So how many more places do I have that have not been choked? 2, right? And out of the 2, I have 7 more distinct letters that are not S to choose from. So that's my choosing done. And then after that, next step, permute the distinct units. So in this case, I have 4 units in total. Of those 4, 2 of them are identical. So 4 factorial over 2 factorial. Same idea as part A. And that is going to be 252. Now, because you cannot have both case 1 and case 2, the fact that these are 2 separate possible cases means that these 2 events are mutually exclusive. So for mutually exclusive events, we are going to use the addition principle. So we just add the number of ways for case 1 plus the number of ways for case 2, and we're going to get 1932. So that's how you do question 1. Now I am going to, before we move on to more complex problems, I'm going to go to another worksheet. So this is revision exercise 1 for UWA 2 your revision exercise for stats S1 and S2, and we start with this particular P and C problem. So we have dealt in the previous problem with arranging objects in a line. Now let us deal with arranging objects in a circle. So let us first draw our circle for part 1. Okay, so actually our circle doesn't need to be so big. Let's shrink that a bit. Okay, so they say one particular girl is seated between two particular boys. Now, the other reason why I chose to include this problem is because please note that people, whenever you are permuting people, people are always distinct. Unless the question says otherwise, which no question ever dares to, because saying people are identical is not politically correct. Anyway, the number of ways in this case is going to be, let us try to draw, right? So let us use pink to denote, actually no, I shouldn't have used blue here. I'll use orange, green. Yeah, so yeah, please note people are distinct. And let us use pink or purple to denote a girl, and blue to denote two particular boys. Okay, so you choose any one particular girl. Let us place her at the top here. And then I have two particular boys. So let us name these B1 and B2. So total I have 9 people, right? So 3 seats are taken. How many more seats do I have? 1, 2, 3, 4, 5, 6. So these seats marked with an X, they can be um occupied by anybody. Okay? So the number of ways to permute these, first, remember, permutes the number of distinct units. So how many distinct units do I have here? Okay, notice that because one particular girl is seated between two particular boys, this box here in orange is actually going to be one unit. They are grouped together. So this is a bit like the situation that we had earlier, where we have this green box over here, I and PT grouped together, they move as one unit. So this counts as one unit, not as 3. And then the other 6 positions marked with an X are all their own units. So how many units do I have in total? 7 units, right? So how do I arrange 7 units in a circle? 7 factorial over 7. Remember this formula? Or you can also write 7 minus 1 factorial. But I prefer 7 factorial over 7 because I find that it's very important to remember that this over 7, the goal of this is to get rid of the rotational symmetry of a circle. And then after that, once I've permuted my distinct units, I can zoom in, look inside this orange box. Obviously, this girl is fixed in position, so she choked her seat already. But what can I swap? B1 and B2 can swap positions, but because it just says she needs to be in between B1 and B2. She didn't say B1 needs to be on her left or right, B2 needs to be on the left or right. So these two boys can obviously swap positions. So I will add a 2 factorial to account for that. And this is going to be 1, 4, 4, 0. Okay, so that's it for part 1. Part 2 is a bit more complex. They say they want the girls to be seated in pairs with not more than 2 girls seated together. So let us draw our circle again. That's very ugly. That's better. Okay, so I have 4 girls in total, right? So let us say I want G1 and G2, 2 particular girls. So we'll treat them as one unit here. And then after that, I have G3 and G4, another 2 particular girls. Once again, box these two, treat them as one unit because they have to be seated in pairs. So each pair must move together. Now, I have how many more seats? I have 1 seat. No, I have another 5 possible seats around the table for the 5 boys. So I can slot here. No, let me use a different color for the slotting. Yeah, let's just use a green. Slot here, or I can slot 1, 2, 3, 4 more. Yeah, so total 5 possible places to slot the 5 boys. But in this case, it's not a slotting problem where we number of slots choose something, because we're not trying to separate the boys. We're trying to separate the pairs of girls. So how do we account for that? Firstly, right, you need to notice what is the assumption that we have made in the diagram when drawing the diagram. We have group G1 and G2 together, right? But do we have to group G1 and G2 together? No. In fact, in order to form the first pair, I have 4 girls. I choose 2 of them to form the first pair. And the pair that and how I form the first pair already directly determines who the second pair is going to be. So that is 4 choose 2 over 2. Okay? And then this one needs to be divided by 2 factorial. Sorry. Now, why does it need to be divided by 2 factorial? Is because you are arranging 2 units around a circle. So these 2 units can swap positions. Instead of here and here, these 2 can terbalik. So this pair can go into this position. This pair can go into this position as long as they stay as a pair and move as 1 unit. Okay? And then after that, obviously, within this group, actually it's still pink lah. Within this units, within this 1 unit, G1 and G2 can swap positions. Likewise, within this 1 unit, G3 and G4 can also swap positions. So I think we're done accounting for the girls, right? Yeah, okay, now let's account for the boys. So for the boys, actually I should have just drawn the slotting arrows in blue, I'm so sorry. Yeah, so the boys, no choice, got 5 more seats. So I have to slot them in these 5. But obviously, these 5 boys, they can permutate themselves in any of these 5 positions. So this is 5 factorial. This is 5 factorial and not 5 factorial over 5, because in this case, you don't need to account for the rotational symmetry. Because since this group chose their position here already, and this group chose their position here already, everything that I've written on top here in pink means they chose already, they fixed their seats already. So you cannot move them any further. That's why you don't need to account for the rotational symmetry of a circle. You just treat it as 5 positions. These 5 boys can sit at any of these 5 positions. So it's 5 factorial. And lastly, we have permuted the girls, we have permuted the boys. We haven't permuted total number of units. So how many units do I have here? 1, 2, 3, 4, 5, 6, 7. 7 units. Arrange 7 units in a circle. Done. 5, 7, 6, 0. Press your scientific calculator and make sure I'm correct. I should be, I think. Yep, okay. So this was a slightly more interesting problem because it also shows you how to deal with the problem of permuting objects in a circle. So I hope you've learned something from these 2 examples on P and C. And now we are going to go on to a slightly more complicated P and C problem. So we are back to the GST worksheet here, back to this GST worksheet. And we're currently doing question 2. So in this particular question, they say that there are 4 houses in a particular school, and each school sends 2 students. Each house sends 2 students, sorry. So 4 houses, each house sends 2 students. Let's interpret the question correctly. And we know that in total there are 8 students. So please feel free to annotate on the question paper. After all, you get to keep the question paper after the exam. And please make sure that you have the correct number of people correct. Or rather, make sure you have the number of people correct. Okay, don't confuse yourself and get the question wrong at the first step. And once again, just as in the previous question, people are distinct. Okay, so keep that in mind. Now, they give you a restriction already in part 1. So this is actually not a very friendly question. Part 1 already got restriction. Okay, it says find the number of ways to arrange the students in a row at the starting line if students from the same house must stand next to each other. Okay, so let's see how we can approach this problem. You will see that because students from the same house must stand next to each other, we can actually treat each house as one unit, isn't it? So how we will do this is we have I have 4 units, right? 4 factorial. So I treat each house. Let's say I have Gryffindor, Hufflepuff, Ravenclaw, and Slytherin. So the 2 people from each house must stand together. So the 2 Gryffindors are 1 unit. The 2 Hufflepuffs are 1 unit. The 2 Ravenclaws are 1 unit. The Slytherins are also 1 unit. Okay, so these two must be together, they must move together. We have come across this concept in the previous 2 examples already. But they don't need to be in this order. You see, right? I can move the houses around. I can move the houses around. So you see that these 4 units, however I move them around, doesn't matter as long as the 2 from each house stay together and move as one pair. So it's just I permute 4 units. That's why it's 4 factorial, not 8 factorial. Understand? And then, okay, we've considered total number of distinct units. So just like earlier, we considered total number of distinct units first, then only we zoom in. So now we zoom in within each box, within each unit. The 2 obviously can permute, right? 2 factorial. And this is the case for all 4 houses. So the 2 Gryffindors can swap positions. The 2 Hufflepuffs can swap positions. Same thing for the last 2 houses. So I have this 2 factorial applies 4 times for 4 houses. So we can save ourselves writing out this term 4 times and just write power 4. Or if you want to use more pen ink by writing this out 4 times just for your own peace of mind, fine. Anyway, press your scientific calculator. This is just 384. Okay, so not very difficult 2 marks to get as long as you think in the correct way. And just as I'm doing here, please draw to help yourself. Okay, don't be afraid to draw. Drawing is allowed in exam answers. If it wasn't, then your answer key wouldn't have a shit ton of drawings. Anyway, it says a house is considered the winner if its 2 students are in the top 3 placing. Okay, I want to talk about this for a bit, okay? If its 2 students are in the top 3 placing. So what does this mean? This means, right, whether I get a 1-2 or a 2-3 or a 1-3, it doesn't matter. As long as they are within the top 3 placing, 就赢了. So whether I get a 1-2 or whether I get a 2-3 doesn't matter. 两个都在 top 3 就是 that house is the winner. Okay, so there are a total of 8 people in the field, right? Let's draw 8 blanks for 8 possible finishing positions. 1, 2, 3, 4, 5, 6, 7, 8. Okay, sorry. So the top 3 is going to be, I use yellow, right? Okay, so let us say this is the top 3, okay? And then they say they want the last 2 students to belong to the same house. So these 2 must belong to the same house. And the thing that you notice, right? Because as I said earlier, no matter whether, let's say house A wins, right? So let's say A1 gets first and A2 gets second. But it doesn't need to be this way. I can also have A1 here and A2 here. Or even A2 here and A1 here. And we can also swap those positions to create even more cases because A2 can finish instead of ahead of A1 instead. So how do I account for all of this? Let's take it step by step, okay? Don't be afraid to think as you write. It's very important in P&C. If you think of some other term, you can just add a times at the back. But also please be careful not to overcount. If you have to write in pencil, annotate in pencil on your solution, this term means what, this term means what. Make sure you understand what you are writing, okay? Don't just anyhow guess, oh, this looks like it should be a 4 factorial, okay? P and C are free marks. Please don't overcount or undercount and lose these free marks, okay? And of course, anything you write in pencil on your exam script that you don't want the marker to mark, please erase, okay? So let us focus on the top three first, okay? So the winning house, okay, can have its two students finish in any two positions in the top three. So out of the three positions in the top three, I just choose two lor. Understand? And then, because I said earlier, right, instead of A1 finish ahead of A2, A2 can finish ahead of A1. So these two can swap. So this is it for the top three. Okay? Next, I can look at the middle four. So, notice, right, that I have four positions, one that is in the top three, and these three in between the top three and the last two, that are, they can be filled by anyone. So the four in the middle can finish in any order. So for the middle, it's just 4 factorial. And then for the last two, okay, you might think it's just 2 factorial and you call it a day. But no, you've missed out on something. Earlier on, what did I start with? I started by saying that house A is going to be the winner, right? So just as I choose one house to be the champion, I must also choose one house to be last. Okay, doesn't sound very politically correct, but the question doesn't care. So, because I've already chosen one house to be the winner, means that how many other houses can possibly be last? 3, right? So out of these 3 houses that can be last, I must choose one of them to be last. And then only the 2 runners from this house can swap. And that is it. So if you press your SC, this is 864 ways for this to happen. Okay, of course, there's going to be a lot less cases if they specify which house wins and which house loses lah. But let's not think about hypothetical situations here. Let's just focus on the question at hand. Anyway, part 3 is where it gets interesting and where I really don't think they should only be giving you 3 marks because there's a lot of new ways that you need to think. But the answer is actually quite simple. Okay? So they introduce a new party here. They introduce the teachers. Okay? So they say each house has a captain and 4 teachers. So they are selected to play in a circle. This is fantastic. We love circles. So they give us a couple of conditions here, right? So they say the teachers from the same house must stand next to each other. So the 4 teachers must stand next to each other. Okay? So if the 4 teachers must stand next to each other, it means that we are going to group them as one unit, correct? So we're going to group them, and the captains must not stand next to one another. So circle back to what we did at the start. Everybody who is well behaved and can be together, we settle first. Anybody who is misbehaving and must be separated, we settle last. Okay? So, by number of ways, for this is going to be okay, how do I want to do this? Let me think for a bit. Okay, so I know that I want to permute the 4 captains last. So first, let us choose the teachers because it says 3 teachers from each house, right? So out of the 4 teachers from each house, I need to choose 3 of them. So 4 choose 3 is my first term. And then these 3 within each unit, so this is still within each unit at a micro scale, can swap positions among themselves. And because there are 4 houses, this term applies for all 4 houses. So I'll stick a power 4. And then after that, we'll not worry about the troublemakers that need to be separated, yet focus on the teachers who can be put together. So I have 4 groups of teachers, each of whom are behaving as one unit. So that's why only 4 distinct units. And arranged in a circle, so divide by 4. And then finally, the captains are misbehaved. So let us slot them out. If you notice, right, I don't have any other colors, do I? No, I don't think I do. Yeah, I don't. Okay. The That was a very ugly circle. Let me redraw my circle, and then I will show you what I mean. Okay, so my 4 teachers, let's say, now I let, so A1, A2, A3 are teachers from house A, right? And then I have another uh group of teachers here, another group of teachers here, another group of teachers here. So that's all my ones in orange. Now, how many more places do I have to slot the captains? 1, 2, 3, 4. 4 only. So it's a bit like earlier, right? How many places do I have to slot the boys? 5. How many boys do I have? 5. So I can only 5 choose 5 times 5 factorial, and 5 choose 5 is just 1. So that's why I only 1 times 5 factorial. I don't think I made that clear enough, right? No, sorry. Let me just add a note onto this question as well. That is because it's actually 5 choose 5 times 5 factorial. So in this case, I have 4 choose 4 because I have to slot in all 4 what? So 4 choose 4 is just 1. And then after that, the 4 in their positions can be permuted among themselves. So it's just 1 times 4 factorial. So just add a 4 factorial at the end. And press your calculator, you should get the astounding number of 4777574. Yeah, I know. When I see this kind of number, I also think, did I overcount somewhere? So it's very important, go back and double check. Okay, but sometimes, actually, a lot of times in P&C, it's not that deep, so you don't need to check too much. Just make sure you stick to your principles. Okay, last question. This is still from the GST worksheet, question 4 of the GST worksheet. And this question is here because I want to show you how to actually use P&C to solve probability problems.